Hey, what's up, guys? How's it going? Today, I want to go through this LeetCode problem. Problem 695 is a max area of island, and this question was asked by DoorDash, Google, Amazon, Facebook, Microsoft, etc. As you can see, so it's a very popular question. So let's see what this is asking. So we are giving a n by n binary matrix. So the value is between 0 and 1, and the matrix is called grid. And then an island is group of ones representing the island. So as you can see, the orange color here is island, and this is all the islands, and this is the darker orange is the biggest area. So the constraint is we only look at four directions. Both the horizon, also the vertical, horizontal and vertical, and also the edges will be surrounded by the water. So we don't look at all the other. So you may assume all the four edges of the grid are surrounded by water. So the zeros are the water, and the ones are the island. So the area of an island is the number of cells with the value 1 in the island. So this is the island, and that's the water. And we turn the maximum area of the island in the grid. So we look at this grid, and we look at the largest area. So which is in this case is 1, 2, 3, 4, 5, 6. It returns a 6, and it does not return an 11 because it only look at like a 4 direction. And so this one is like a diagonal relationship, and it does not belong to this island because we only look at the 4 adjacent and up, down, on the left and right. So this is a diagonal, so it belongs to a separate island. So it returns 6, and we will try to solve this problem with 2 approaches. And the first approach is as we can see in here. So a little bit like a brute force approach. So first we are defining the total number of rows. So the grid. So as you can see, the input so is a list, and the list of lists. So each of the individual lists is individual row. So we can say 0, 0, 1, 0, 0, 0, 0, etc. And then that's the first row. And then the second list of the grid is the second row. As you can see, so this one corresponds to this row. So what we did first is to look at the maximum number of rows. So total rows equal to the length of the grid, and total columns, we just look at one of the rows, and then look at how many columns in there. This is the length of a column. Look at the first row. First row. And then we have a set, and we call it scene. So this is collecting all the coordinates that we have seen before, and then so we don't duplicate the work, which is low. So fairly straightforward function. So we are defining another function within this function. So we call it 4 direction area, and it takes in 2 arguments. One is a row, another one is the column. So we keep track of the coordinate, which will be arguments. So if the row is less than the total number of rows, minus 1 because it's index, and between 1 and 0 and total number of rows minus 1, so we don't go off the edge. Same condition for the column. Make sure that it does not go off the grid. And if the element that we're looking at is equal to 1, so we don't look at the water, and this coordinate is not in the scene set. So if these four conditions are satisfied, and then the set, we will be seeing this particular coordinate. So we're adding this coordinate to this scene set. So we add to it. So again, we don't duplicate the work. And then we return 1 plus the 4 adjacent cells, right? So will be row minus 1 will be the one above, and row plus 1 will be the one below, and column minus 1 is on the left, and then column plus 1 is on the right. So and then plus 1 is itself. So for instance, if we look at this guy, and if this this is a recursion function, it's keep calling itself by but the input will be the adjacent coordinate. So we look at the first one, and then look at all the adjacent one, and each time you add to the scene. So when in the future, when this cell is looped, so it wouldn't be done again. So this is how this works. And if this either one of these conditions is not satisfied, we will return the 0. So either you go off the edge, the grid, or if we look in the water, we look at the number 0, or we have seen this guy before, and that will return a 0. So we don't duplicate the work. And after we have this function, and we can loop through all the elements, and to look for the maximum. So for each of the row index in the range between 0 and total row minus 1, and also look through each of the column index, and we initiate the maximum area to be 0 before we seeing anything, and then we keep calling this function for each one of the we are seeing. Of course, if we something we have seen before, and then we just bounce back by this condition. So, and then at the end we return the maximum area. So performance-wise, it is a 136 millisecond, and also the memory. So it is faster to 50%, and this is the memory usage. So let's talk a little bit about the time complexity and the space complexity. Time complexity, as you can see, mostly from here. So we calling this 4 direction area, and then looking through all the the row coordinate and the column coordinate. So we'll be big O of number of rows times number of columns, and space complexity will be the scene set. So we keeping track of all the coordinates we are seeing along the way. So this takes up the space complexity. So this is one approach, and the second approach is to apply the depth first search. So this is that solution. This is a slight improvement in terms of performance, as you will see later. So initial setup is the same. We're looking at the total number of rows, total number of columns, max area, and scene set, same thing. And then we are looping through the first. We use an enumerate to loop into, and it comes back this is the entire row, and also the row index, and will be the list for each individual row. And then within that individual row, and then also we looping through the column index, also each of the element within that entire row, entire R, so entire row list. And then if this coordinate has not been seen before, and then we are seeing it right now, So we add to it. And if regardless if this is 0 or 1, because we are seeing it, so we don't duplicate the work. If, and then we go one step further, if the element that we're looking at, if this is a land, not the water, and then we initiate a stack. And then the stack initially just take up one element, it's a list, take up one element, which is the, it's a tuple, it's a row index and column index. And then the initial area, and then we initialized an area, which is 0, because we haven't seen the land, not yet. So, and then while the stack list is not empty, if there is something on it, and then we pop up a item format, so we call it item. And the item, the first item will be the row index and column index we're looking at, and then we extract the element. I call it R and C, which is is the row index and column index. I just want to separate it from this R IDX and C IDX to avoid confusion. Basically, we are extracting the information, the two coordinate, the row coordinate and column coordinates from this item. Look at the first component and the second component, and the area. So that area that we initialize as a 0, now we adding the grid number on it. So because the grid number is 1 in the beginning, so we're adding that number, and then we applying the depth first search. Look at the neighbors. So for example, for this guy, and then we look around for the 4 adjacent neighbor. So row -1 would be the one before, row +1 will be the one down below, column -1 is on the left, column +1 will be on the right. Then work with all the neighbors, the 4 neighbors. And if this is within the boundary, does not go off the edge of the grid, 2 conditions, both for rows and column. And then if this coordinate is not in the scene set, has not been seen before, and then if that element is a land, the value equals to 1. So what we do, we put this coordinate appended to the stack, and then now we are seeing it, so it becomes the scene set and not to duplicate the work. And then after we add it to the stack, and then this one we will run it again, will be in the loop until the stack list is empty, and then we do it again and again for all the neighbors, the qualifying neighbors. And then after we have the area which collects all the collects all the numbers. This one is only execute when the first element is 1, and then we apply a max function. It's basically a running, sort of like a running total kind of thing, running max. So and then we compare the prior result to the current result, and then look at the best one, and then we return the max area at the end. Performance-wise, this is slightly better than what we had before. So we faster than 70%, and the memory usage is less than almost 90% of the Python submission. So in terms of time complexity and space complexity, time complexity, you can see we looking through all the row index and column index, and also look around the neighbors. And whenever we're looking around, we mark it as seen. So this will be O of number of rows times number of columns. So not the big O of all the number of elements in the grid. So that's a time complexity, space complexity. is same as what we saw in the prior solution, and we have to keep track of all the coordinates. So that takes most of the time, the space complexity, and again, this will be O of a number of elements as well. And this stack list takes a little bit of space as well, because it's looking around the four adjacent coordinate. So the worst case will be everywhere is 1. If everywhere is 1, and then the space complexity will be big O of a number of elements as well. Okay, so this is so much for this LeetCode problem. I hope you like it, and if you do, please consider hit the like button and subscribe to the channel. And thank you for watching this video, and see you next time. Bye bye.